If you have followed our rocket-powered paper glider experiment videos, then you know we've been hard at work developing and testing components for a high-performance two-stage water rocket project, which we have named Project Gemini. An important part of this project is the development of a two-parachute dual recovery system that will help us ensure a safe recovery. The main reason which we chose to use a complicated system like this is due to the fact that the launch days with perfect wind conditions for launching high-altitude water rockets are very rare. A typical rocket launch with a single parachute will deploy at apogee, and it can potentially drift a long distance due to the wind currents while it descends. This may cause the rocket to land in an undesirable location or become lost altogether. With a dual deploy parachute system, the rocket can deploy a small parachute at apogee, giving it a more rapid but controlled descent. Once the rocket has descended closer to the ground, it can deploy a second, larger parachute, which will land it at a safe speed without drifting very far. In this video, we're going to develop and test a water rocket with a dual parachute recovery system for Project Gemini. For this project, we decided to modify an existing rocket that we had already flown to save some time and effort. The rocket that we chose was a design that was comprised mostly of 3D printed parts. Even though just about everything except the bottles were 3D printed, the design is very similar to our other rockets, and it goes together very much the same way. This rocket originally had a single deploy parachute system installed on top of the pressure vessel. The system which was used for it was our radial deploy mechanism, which is triggered by our do-it-yourself launchpad altimeter, both of which we have covered in detail in previous videos that you can find in the links below. The rocket had an existing threaded joint near the bottom, where two spliced bottle sections were joined together by one of our 3D printed tornado tubes. This joint forms the perfect location for another radial deploy mechanism to be added for a second parachute. For simplicity, and also for redundancy, we put a second altimeter and servo with a separate battery in this deploy system. That way, if either one of the systems had a malfunction, the other one would still deploy at least one of the parachutes. This redundancy paid off later, which you will see shortly. The smaller parachute is often called a Drogue Parachute, and it deploys at apogee, like a typical single parachute recovery system. For this rocket, the Drogue Parachute altimeter can use the standard off-the-shelf software. Our standard altimeter software does have a timer delay function that we could have used for the second altimeter to delay the release of the larger main parachute, but the customized version of the altimeter software under development for our staging mechanism allows for custom trigger events. In this case, the deploy trigger was defined as the altitude descending and altitude less than 200 feet. This means that the parachute would deploy if the rocket was coming down and the altitude happened to cross 200 feet. Keep in mind that there's no reason that a reliable system similar to ours cannot be achieved using the other parachute release mechanisms available, such as air flaps and Tomy timers. But we wanted to get as much use out of the work that we put into our custom altimeter. The setup and arming procedure for the dual deploy system is exactly the same as it is for a single parachute rocket, except for the fact that it must be done for two parachutes instead of just one. That should be very easy and hard to mess up, right? As soon as we had good weather, we decided to test launch the system and see how it performed. Here's how the testing went. The inaugural launch did not go so well. If you look closely, you can see that only the main parachute deployed. The rocket was spared severe damage because the one parachute did work as expected, so we at least proved the benefits of redundancy. From the onboard camera video, we discovered what went wrong. We simply forgot to arm the second altimeter. You can hear the altimeter beeping the previous altitude through the entire flight, indicating that we just never armed it. We learned from that mistake. The rocket was recovered and prepared for a second test launch. This time we made absolutely sure that both altimeters were armed before the launch. This time it was going to work. Okay, so you know that was not supposed to happen. Both altimeters were definitely armed. We triple checked. When we reviewed the onboard camera footage, we saw immediately what went wrong. We accidentally installed an altimeter in the rocket which had previously been programmed with a long deploy delay. The altimeter detected the correct trigger for the drogue, but then it began a delay timer before releasing. The audio tones that the altimeter makes when it is in delay mode are clearly heard while the rocket is descending. The rocket impacted before the delay expired and the parachute deployed. We did not intend to use this altimeter with a delay, so it was just another human error and not a fault in the system. We recovered the rocket and made some minor repairs. This time, we carefully checked the altimeters to make sure that all the settings were correct. Then we armed the rocket and prepared for a third launch. Now that's more like it. This time the system worked perfectly. The altimeter graph shows that the two parachutes did their jobs and the descent rate was controlled exactly as was intended. The rocket came down quickly at first and then slowed down for a soft landing. The experiment was a complete success. For this experiment, we had been hoping to get a unique view from the onboard camera by attaching it to the shroud lines of the drogue parachute looking down so we could see the descent from an overhead perspective. But the video came out terrible, because the camera was buffeted around by the wind. We improvised a separate stabilizing shroud line for the camera to try and get better video on the next flight. There was plenty of time left to try again, so we went for it, hoping to get the money shot from the overhead view. Once again, we armed the rocket and attempted another launch. This time we uncovered a new problem. The drogue parachute deployed, but it didn't inflate. The rocket surely would have crashed had we not been using a redundant parachute. The redundancy of the dual recovery system has saved this rocket 3 times so far, so it has paid off well. Why didn't the drogue parachute inflate this time? Well, from the video footage, it appears that our clever stringing system to attach and stabilize the overhead view camera had become entangled with the fins and prevented the drogue parachute from opening. Only the main parachute deploying at a low altitude saved the rocket from crashing. In conclusion, we can say that we learned a lot from this experiment. It's pretty clear that the idea of using a dual parachute system does help ensure that the rocket does not drift from a high altitude. and it has the side benefit of providing some redundancy. We also learned that the concept does add complexity and increases the chances of human error. This experiment was definitely a success and gave us some additional ideas for variations on this design that we could evaluate in future flights. Do you have any ideas or suggestions for what you would like to see us test? Discuss your thoughts in the comments below. We would really like to know what you want to see in future experiments. If you enjoyed this video, give us a thumbs up to let us know. And if you're stopping by the channel for the first time, please subscribe so you can follow along as we conduct more of these experiments. Thanks for watching. We'll see you next time.